So this is a disjoint union. A cap B. From the axiom 3 of probability measure, disjoint union can be expressed as the sum of probabilities. No, so the law of addition here. They are disjoint, so we can split into the summation. Okay. But this probability, this set is equal to A, so this is equal to probability of A. But using the definition of conditional probability, we have probability of A given bk times probability of bk. So that proves the theorem. Okay. Any questions? Oh, some students are offline. Okay. No question. Okay. Okay, then let's change a topic. So far we have been very theoretical today. Maybe it's exhausting, so let's look at more concrete examples. So here is a data of let's see, 20,000 throws with 2 dice. So there was an astronomer, a Swiss astronomer called Wolf, and he did experiments of throwing 2 dice 20,000 times. He did this in 1850, and this is the result. This is the result. Okay, so this means he had 2 dice. One is red, the other is white. Okay, and out of 20,000 throws, he got one on red and one on white, on both 547 times, and one on red, 2 on white, 587 times, and so on. So this is the result of the experiment. Right. So by looking at this table, of course, there are some statistics already calculated here. The total of this row is here. Total of this column is here. And the proportion. So this 0.170 is calculated by dividing this number, total number, by 20,000. Okay, and so on. So from this, can you tell that these dice are biased? Now, of course, in each die, there are 6 faces, right? So 6 faces, like, I don't know, something like this. 6 faces. And if this is not biased, each face of a die will appear with probability of 1/6. So by looking at these numbers, can you tell this is biased? These are biased. By the way, what is the value of 1/6? It is approximately 0.16666. So let's say this 167. So if these numbers are close to this, then they are not so much biased. But it looks like this is and this is also quite a huge deviation from this. How come? This is a lot smaller. Interesting. Can you come up with some theory explaining this deviation? Or is this just a chance? Well, I hope we will study how to analyze this data later in the semester. There can be many things we can do with this data. That's one thing. And what about how we can calculate the score of the total score of the probability of total score of dice? Okay, so score means the sum of two numbers in two dice. So 1 plus 1, if we get 1 and 1, the score is 2. If you get 1 and 2, the score is 3, and so on. So can you calculate the probability of the scores if the dice are not biased? Okay, that can be calculated by counting the ways to obtain the score. Okay, there are, I think, 11 possible scores. The sums are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you get 1 and 1, you get the sum of 2. If you get 1 or 2, 1 and 2, or 2 and 1, you get sum of 3. And so on. And if you get 6 and 6, you get sum of 12. And this column, ways, shows the number of ways to obtain that score. To get the sum of 2, the only way is to get 1 and 1. So the way is 1. Okay. In order to get the sum of 3, there are two ways. So red and white die give the score of 1 and 2, or 2 and 1. So there are two ways. What about 4? 4 means 1 plus 3, or 2 plus 2, or 3 plus 1. So there are three ways. So you can calculate this way. Then, if the dice are not biased, each possible score can give you the probability of 1 over 36. And so you multiply the ways to obtain the score, you get the probability of getting that score. So in this case, 2 times this number, this. 3 times this number, you get this. 3 over 36, and so on. So you compare these theoretical values with the experiment. So they are somewhat close. But are they close enough? How do you judge? By the way, how do you get this number from experiments? Now, these numbers are obtained from this table. Okay, so this number, sum of two, 0.027, is obtained by dividing the number, this number 547, by the total number of experiments. Okay, and so on. So these numbers divided by 20,000, you get these numbers. And of course you have to add them. So in case of sum of 2, there's only one possibility, but in the case of score of 3, you have two possibilities, this and this. So you add them and divide by 20,000, you should get this number. And the sum of 7, there are 6 possibilities, so you add 6 numbers. Sum of 7 means, for example, let's see, 1 and 6. Let's see, 1 and 6, 5 and 2, 4 and 3, 3 and 4, 2 and 5, and 1 and 6. So you add these numbers and divide by 20,000. Okay, and this is a probability. These are probabilities calculated based on theory and experiment, but both satisfy the axioms of probability, by the way. You should check. So in this case, what are the sample space? What is the sample space, and what should be the sigma algebra? And what is the probability measure? How do you define the probability measure? Okay, so the sample space would be the set of pairs of numbers where, okay, omega, set of pairs of numbers where k and l are integers from 1 to 6. So this will be the sample space. For sigma algebra, we simply define the sigma algebra as the power set. So that means the set of all subsets of this. Okay. And by the way, what is the cardinality of this omega? Since k and l can vary from 1 to 6, there are in total 36 elements here. Okay, and how do you define the probability measure? Just define as the cardinality of any element of f divided by cardinality of omega, which is 36. So this 36 comes here, right? And how, so this is for theoretical calculation. What about the experiment? In this case, what is the sample space? Actually, this is not so trivial because, in experiment, there are 20,000 samples. So this sample space is clearly different from the sample space we have just described. Okay? Okay, think about this. Okay. Okay, that's all for this dice problem. And let's talk about